Now that we've created these different types of distortion effects, let's look at a couple different ways that we can analyze their processing. First, let's compare the amplitude of our output signal to the amplitude of our input signal for the different nonlinear functions. Then, let's save some of the processed signals as audio files that we can load in Pro Tools and look at the harmonics that are created by the different distortion effects. Now that we've been able to create these different distortion functions, let's go through and analyze the processing that occurs by comparing the output amplitude of the processed signal to the input amplitude. I'm going to make use of this script we created previously for testing the different distortion functions. I'm going to start out by working with this full wave rectification function. So I'll uncomment this line, comment out the other ones. What we're going to do is use this input signal here. It's a sine wave with a frequency of 3 Hz. We can look at the waveform then by plotting the input and the output here, separate commands. So I'm going to call this figure 1. We're going to plot the waveforms. Then let's create a second figure window. Call it figure 2. We'll actually plot these side by side. In this case, what we want to do is compare the amplitude of our input signal as the first argument for a horizontal axis. We're going to plot that compared to the amplitude of our output signal. And just for comparison, I'm going to put in here that we'll plot our input versus our input. So actually we'll end up with 2 separate lines. This first one here should be a straight line from -1 up to +1. Then we'll look at the different nonlinear curves that get created when we plot our input compared to our output. So first up, we have our full wave rectification function. I'll run the script and look at the plots. So here I'll put these side by side. We can look at. We've seen this one before. It's our waveform for the input and output signals. We have our blue sine wave and then our red distorted signal, where the negative amplitude gets reflected up to positive amplitude. So what does that look like when we start to plot the output amplitude versus the input amplitude? We have these lines instead of looking at the waveform. So our blue line is our input signal without any processing, goes from -1 up to 1. We can see the distortion that occurs when we have any negative amplitude down here gets reflected up to be positive amplitude. So if we had an input amplitude of -0.5, our output amplitude is going to be positive 0.5. So we have this discontinuity here that is indicative of the fact that we have a nonlinear functions. It's not just a straight line all the way across our full scale range. As you may have seen this before, our full wave rectification function is also the absolute value function, where you'd see this kind of shape to it. So let's move on and look at another function. So we'll comment out full wave rectification. Now we can plot half wave rectification. This is the case where we're going to take our negative amplitude in our signal and cut it off here at a value of 0. So what does this look like over here? Our output, our red line, is going to have a value of 0 anytime our input amplitude drops below 0. So for all these values within this range, have an output level of 0. It's half wave rectification. Now let's look at infinite clipping. This is where we take our sine wave and turn into a square wave with a maximum full scale range of 1m-1. So what does that look like over here? Anytime we have a negative amplitude on our input signal, our output level is going to be -1. Anytime our input signal goes above 0, we end up with +1 up here for our output level. That's infinite clipping. Next up, we can look at hard clipping. So in this case, we set some level, like 0.5, that our amplitude gets clipped off. Over here, we can see that we have a linear relationship within this region of operation in between the thresholds. But then when we go above that threshold of 0.5, everything gets clipped off and our output stays at a level of 0.5. It doesn't go above this level. Same thing down here. It never drops below this level of minus 0.5. It stays there even if our input signal goes lower. So that's the hard clipping. Next up, let's look at soft clipping. So in this case, we're going to gradually round off and smooth the top of these peaks out so they never actually reach the full scale range. What does that look like over here? Have a nice linear relationship when we're close to 0, but as we increase the amplitude, it's going to round things off. Instead of going all the way up to a value of 1, we have this nonlinear kind of curve. So that's one type of soft clipping. We can compare that to then the arctangent distortion. In this case, we end up with a nice smooth curve, but it's different. It's going to cause a different kind of distortion sound. So in this case, we're going to have a sharp rise in the amplitude of our signal when it's low compared to our one-to-one relationship. You can see that it's above the waveform here, but then our peaks are also going to get rounded off. So that's the arctangent distortion. We also have the ability, in this case, to control the amount. We have this alpha value. I could lower that down to 3. We see that it's not as dramatic kind of a curve. It's closer to then our undistorted input signal here. So that's the arctangent distortion. Lastly, we can look at bit reduction. So in this case, we're going to take that nice smooth sine wave and end up with this stair-step kind of signal where only certain amplitude levels are allowed. You can see the same thing over here. If we zoom in on this value of 0, as our input signal goes above the value of 0, our output signal is going to have this value of 0.25 for all these different input signals over this range. And then when our input signal jumps above 0.25, all these different input signal amplitude levels get rounded up to 0.5. So we end up with this stair-step kind of signal here. Can change the number of bits. How about 5 bits? See that we end up with more possible amplitude levels. As we increase the number of bits, be about 12 bits, you can see that our stair-step levels start to be closer and closer to this straight line. So that's our type of bit reduction or bit crushing distortion. Another thing that I'll point out here before we switch over and analyze the harmonic content of these distortion algorithms, is we can look at these nonlinear curves and the symmetry that's associated with them. So let's go back here to our hard clipping function. We look at this plot comparing the output to the input amplitude. If we focus in here on the origin of 0 on our input and 0 on our output, we can consider what's happening over here for positive amplitudes. See this kind of shape that occurs. We can see that it's symmetrical if we rotate it around and look at it down here for negative amplitudes. We get this kind of shape here and the same reflected shape or rotated shape down here. So that's one kind of symmetry that we can see. Let's go back and look at full wave rectification. So in this case, we still have symmetry, but instead of rotating it around, whatever's happening over here for our positive amplitudes are rotated down here for negative. We actually see it reflected so that whatever is positive here, we have a positive amplitude. But then when we go negative in our input signal, we actually have positive amplitude over here. So it's not rotated around, it's reflected over. These two types of symmetry that we can see in these functions have different names or are described as being related to even functions and odd functions. So in mathematics, we have these type of functions. An even function is such that our level over here for our negative numbers or negative amplitudes are equal to the positive amplitudes. It's reflected over this y-axis right here, going through the origin. So we see this reflection. And that's an even function. We go back and look at one of these other ones that has the other type of symmetry, a rotated symmetry. So when we have a symmetric kind of curve that happens over here for our positive amplitudes, that's down here with our negative amplitudes, this is called an odd function. There's rotational symmetry to it. So these are important things. If you go back through and think about the different functions from bit crushing to soft clipping, hard clipping, full wave rectification, think about those different types of functions. And now we're going to switch over to Pro Tools and look at a different way of analyzing them based on their harmonic distortion that occurs. So in order to do this in my MATLAB script, what I'm going to go through is save some of these signals as actual audio files. So I'm going to use this command audio write, where I put in a file name. How about sine wave? I'm going to put in our input signal and our sampling rate. So now we have something to compare. We'll have our unprocessed signal, and then I'll go through and save an audio file for these processed output signals. Let me make a comment in front of these commands. So we'll save our input signal, this time through with audio write. Then I'll copy this command, put it down below, and we'll save our full wave rectification, so our output. One thing that I think might be helpful is for us to use a higher frequency. So why don't I go back here through beginning and change this frequency from 3 up to 100. I think that will be easier for us to visualize when we're looking at it in Pro Tools. So let me run the script again. Now we'll save a sound file for full wave rectification. And then I'm going to go through and save a different sound file for each type of distortion. Now we can open up these sound files and import them into our digital audio workstation in order to analyze the harmonics that are created from the different functions. Here in Pro Tools, I've imported in all of the sound files that we created in MATLAB. What I'm going to do is go one by one and play them back. Using this spectrum analyzer, we'll visualize the harmonic distortion that gets created by each of the nonlinear functions. Initially, I'll start out by playing back our unprocessed sine wave signal. This is a 100 Hz tone. So on our spectrum analyzer, we see a spike that occurs here at 100 Hz. Now let's look at some of the distortion functions. First up, a good one to understand is this infinite clipper. This is where we take our sine wave. In this case, the distortion actually turns it into something that's like a square wave. We've looked at the harmonic content of square waves before to see that we have the fundamental frequency here at 100 Hz, and then we have harmonics as we go up the spectrum that decrease in amplitude. Looking closer, we can see that these harmonics occur at odd multiples of our fundamental. We have 100 Hz, 300 Hz, 500 Hz, 700 Hz, and so on. Remembering back to what we looked at in MATLAB, this type of function will be described as an odd function. There's this rotational symmetry such that whatever is happening to the positive amplitudes, we have a similar thing happening to the negative amplitudes. So this odd function is going to give us odd harmonics. Let's move on and look at full wave rectification. This is again where we take the negative amplitudes and make them positive. This is a different kind of symmetry. This is an even function. So when we plot this one, we get a different kind of harmonic spectrum. Here, the spikes occur at the even multiples of our fundamental. 200 Hz, 400 Hz, 600 Hz, 800 Hz, and so on. In fact, we don't even have our fundamental at 100 Hz in this case. Looking closer here at our waveform, let's consider how often this sine wave repeats a period. So it's going to go through a full cycle here where it goes positive and negative and then starts over this same pattern again. Now let's look at the full wave rectification. In this case, the pattern that gets created here of increasing in amplitude to be positive, then it starts a new cycle over again. That's going to increase in amplitude and so on. So in this case, our period is actually half the amount of time. Therefore, our frequency is actually going to go up. So now we're going to have the lowest frequency is 200, or twice what the original frequency is here of our sine wave. So that's a function that gives us even harmonics. Now let's look at half wave rectification. So this is similar to full wave rectification, with the difference being we still have this fundamental here at 100 hertz. And we do have these even harmonics, 200, 400, 600, 800, and so on. So looking again at our waveform, we see that this pattern that gets repeated of the cycle still occurs at the same time period as our sine wave. However, the distortion that's happening is going to give us this kind of harmonic relationship. Now let's move on to hard clipping. Hard clipping is another type of an odd function. Whatever we have going on the positive amplitude, we get a similar thing for the negative amplitude. So we've gone back to another function with odd harmonics. There is a difference here if you look at the waveform of our hard clipper compared to infinite clipping. In this case, the amplitude of these harmonics rolls off at a quicker rate than it does for infinite clipping. Here, with our square wave type signal, the amplitude of these harmonics stays higher. But when we go to hard clipping, it's not going to sound as harsh. The amplitude of these harmonics falls off at a quicker pace. We can compare this function then for hard clipping to soft clipping. First up, we'll look at cubic distortion. This is a type of soft clipper. Again, this is an odd function, so we'll get odd harmonics. However, in this case, when we take the signal and use the cube of the signal as part of the function, we're going to end up with this spike here at the third harmonic. We've got a spike at 100 hertz and 300 hertz. In fact, the amplitude that we use for the cube of our signal is going to determine how high this amplitude is of our third harmonic. If we decrease the amplitude of that cube part of our function, it's going to decrease this spike. Next, let's look at arctangent. This is another type of soft clipping with odd harmonics. We can see that we get a lot more harmonics. Rather than just a single one, we can use this kind of hard clipping if we want more of a rich harmonic spectrum to the distortion. So just another choice between one type of distortion and another. Lastly, let's look over here at bit crushing. In this case, bit crushing is actually still going to be an odd function, where the positive amplitudes are similar to the negative amplitudes. So we primarily get here our odd harmonics, 100, 300, 500, 700, and so on. In this case, one thing that's different is there's not an obvious pattern or roll-off to what's happening with these harmonics. In fact, up the spectrum towards Nyquist, we're still going to have these harmonics that occur at a relatively similar amplitude. So this is a reason actually why it's important to do things like dithering whenever you're changing the bit depth on a signal. So that concludes our analysis then of our distortion functions. We've looked at it in two different ways: how we can plot the amplitude of our output to our input and look at the kind of distortion nonlinear curve that occurs, and then also look at the harmonic distortion here using a spectrum analyzer.